essa agora é a segunda sessão do curso do professor Samuli Siltanen. E a última aula vai ser, então, amanhã no mesmo horário. Okay. Please, Professor Siltanen.
Thank you very much. So, welcome back. This is the second part of my introduction to the mathematics of sparse data tomography. And today we'll see a couple of real-world examples, how these things work. And also, let me begin with, well, first, again, the advertisement of our Center of Excellence. Then we thought about the MATLAB session with Alexander and Markus, and we are suggesting that tomorrow, after the lecture, any one of you who is interested, please let Alexander or Markus know, and we'll get together then and give instructions and help working with these codes and open data sets. And also, let me give you some links to resources. These links are live links, so you can click them in the slides PDF that will be available in the course website. So we have, let me also show from here. So this is the Finnish Inverse Problem Society page. So this is the address of FIPS. And at FIPS, we have several different kinds of open datasets, including computed tomography datasets. So if you click this one, you find a page like this. So there will be the Lotus dataset we saw in one video. There will be and some walnut datasets, and also a cheese dataset we carved out of cheese. And for these, you see how they were measured, and you can download the data and matrices and start working with the data in MATLAB. We try to make it as easy as possible at FIPS, so please let us know how the datasets work for you. Then we just started a computational blog with the Finnish Inverse Problem Society. There are now 2 entries. I think they are also listed in the webpage of this event. So there, if you go to so this is the computational blog, and here there are a couple of entries I created especially for this course. So you can find these truncated SVD things with all the codes and explanations. And also I listed here a few pages. This MATLAB page of my book with Jennifer Mueller, there are kind of codes very much related to the ones used in this course. And then there is a couple of others. The Astra toolbox was developed by Dutch and Belgian researchers. It's a really nice, very large-scale data set of, not data set, but I mean algorithm collection for tomography. And also Per Christian Hansen's group in Denmark has built this TV-Reg resource. So there are a few points where you can start building your codes upon. Okay. So today's program will be, there will be 2 real-world case studies. First thing we did with university hospital physicists in Oulu University Hospital. And in the end, there will be a dental imaging example coming from my period working in the medical imaging industry. And in between, I'll tell you a little bit about wavelet and shearlet-based reconstructions with quite a new approach we just published for automatically choosing the regularization parameter. Then also I would like to talk a little bit about the back projection and the transpose matrix of A, and also give a very short derivation of the filtered back projection algorithm. And then before going to the dental case, which is based on limited angle tomography, I want to discuss a little bit special features that make limited angle tomography even more difficult than usual sparse data tomography. Okay, so that's kind of today's agenda. So first, I would like to describe this very recent work we did with these people. So Tatjana Bubba and Zenit Purisha and Juho Rimpeläinen, they are at my university. And then from Oulu, we have Simo Saarakkala, Miika Nieminen, Juuso Ketola, and Sakari Karhula. And also from Berlin, Maximilian Merz was visiting us in Helsinki. He's an expert on shearlets. So what we did is we wanted to help the hospital physicists to study imaging of bone samples. So one of the specific things they want to do is to detect something called osteoarthritis, which is some kind of bad condition of the bone. I'm not a medical expert, so don't ask me about what's there, but we can clearly see that something not so nice is going on with this bone. And also, let me remind you here that I would say that one of the take-home messages of my course is that when working with applied inverse problems, it's important to find out from the end users what is it that they really want? What is their problem? Why do they need the computational inverse problem algorithm? And check with them if they are happy with the outcome. I mean, then in applied mathematics, in my view, it's the end user that will decide whether our solution was good or not. So it's not an internal mathematical decision, but the judgment if the research was successful depends on the end user. So here we tried to help them, and the thing is that they have small bone samples. So this is a 3D reconstruction of one of the samples. It's about 2 millimeters the diameter here. So they have these very small samples that they put into micro CT machines that are kind of desktop machines that rotate the sample and make a 3D or collect data from many directions. I think the standard imaging procedure takes almost 600 angles. Well, it takes a long time. They have to do lots of these samples a day, and they would like to do it faster. So then they were asking us if some modern reconstruction method would make it possible to collect only much less of those angles and reconstruct from there. So that's what we tried to do here, to reduce the angles to make the imaging sequence faster. So this is what they do. Actually, they're not so interested. They are not so interested in the 3D reconstruction with all of its details. In this application, they want to find out a couple of quality numbers about the condition of the bone. And the quality numbers are computed so that first there is a thresholding operation. So then the three-dimensional volume will be binary. So there is just two possible values, 0 for empty space and 1 for bone. And then they look at several different quality numbers. Here I'm showing two of the most important ones. So there is this trabecular thickness number that shows the maximum radius of a sphere that can be fitted inside the bone area in the binary bone representation. And there is the trabecular separation, which is the greatest sphere that can be inserted in the empty area. Kind of measuring this measures kind of how much there is bone, and this measures how much there is not bone. And now if we use only 40 of those angles we measured, with the idea of maybe we can measure only 40 and make it faster. Now if we use the classical method, the Feldkamp-Davis-Kress FDK algorithm, which is kind of a cone beam adaptation of the filtered back projection algorithm, we see that there will be a lot of artifacts. And after thresholding, the algorithm really thinks that these pieces here are bone, and these black pieces here are not bone. We implemented a sparsity promoting reconstruction based on three-dimensional shearlet transform. And once we do that from those 40 angles and then threshold, we get this one, which is much better. It doesn't have all of these artifacts. It seems to be kind of better. But again, what is it that the end user wants? It's actually not such a picture because it's fed into an automatic analyzer that measures these sphere sizes I was talking about. So actually, we need to measure the quality by feeding the results into the analysis software they have and see if they get consistent results. So here I'm showing these trabecular thickness and separation values for healthy bone. And here, by the ground truth, I mean here I used all of those 600 directions and got a very high quality reconstruction and very reliable numbers. So for healthy bone, we see that inside the bone we can put a bigger sphere than for the sick bone. And then in the healthy bone, outside the bone, only a smaller sphere can be fitted compared to the sick bone. So we see that when this condition appears, the trabecular thickness becomes smaller and the separation becomes larger. And it's these numbers they want to see from the samples, and hopefully with a faster imaging procedure. So then we checked first with the FDK algorithm that we saw that contains those noisy things. And now we see that if we compare to the ground truth, when we start to throw out the data, so instead of these almost 600, we use only 120 or 60 or 40 projections, we see that computing these numbers with the automatic software becomes very unreliable. When we use less and less projection data, we're not getting the right numbers anymore, which is kind of understandable. You know, if we have something like this, for sure the automatic algorithm will fail. So this is not so promising with the FDK, but now when we use the shearlet-based method, you see that even when we throw away data and use only a subset of the measurements, we quite consistently get almost the same number. There is some error, but not too much, and there's not so much change even when the data becomes sparser and sparser. So this is one example that we can speed up their workflow, which is what they were wanting, and we can measure if we can deliver to them by looking at if we can give them the right numbers even with less projections. So that's my first real-world application case, and also it also contains something that we will also see in the dental imaging procedure.
Samuli.
Yep.
Is there any strategy for choosing the projections if you use only 40 instead of 500?
Sorry, can you repeat the question?
Is there a strategy for choosing the 40 projections that you're going to use instead of the original 500?
Well, we just, in order to avoid limited angle tomography, we choose those 40 angles in the full circle. So we make them span the whole circle because limited angle tomography brings its own difficulties. So we are doing a full angle, but sparsely measured angles. Yeah. And let me explain you a little bit about this regularization method we use for this case. First, I'll explain it with wavelets because it's simpler, and then I'll a little bit tell how it's changed to shearlets. So our starting point was this paper I mentioned already on Tuesday by Dobeshi, De Vries, and De Mol, where they provided a proof of this iterative sparsity promoting regularization method where, let's see, so the goal is to minimize this kind of regularization functional, where this is the standard data misfit term. And here we have a wavelet transform of f and one norm. So this is actually just the sum of absolute values of wavelet coefficients. And since there is this one norm, minimizing this kind of thing is known to promote reconstructions where a small number of wavelet coefficients is non-zero. Most of the wavelet coefficients are 0. And then, of course, the bigger you make mu, the more you have 0 coefficients. So Dobeschi, de Vries, and de Mol used convex analysis to design an iterative solution method or computation method for the minimizer of this functional. And it's done with this quite simple iteration that inside it has the data discrepancy here, back projected, summed up with the current iterate, then wavelet transform, soft thresholding, and inverse wavelet transform, and that's the iteration. And as we saw on Tuesday, the soft thresholding is putting all wavelet coefficients smaller than mu over 2, it's putting them to 0. And the soft here means these two extra terms that make this operation a continuous function from the real line to the real line. Okay, in our work, actually, we wanted to also have the non-negativity constraint. We wanted to project in every step of the iteration, we wanted to project, or let's say, replace any negative pixel value by 0. That's what we want to do to keep our result non-negative according to X-ray physics. So then we found out first this paper by Loris and Verhoeven, and then actually this by Chen, Huang, and Zhang, where they generalized such an iteration, sparsity promoting iteration, to the case that can rigorously include the non-negativity projection. So let's see what happens here. There's an extra variable. So we have f here, but then in addition we have these v and y in this iteration that has a couple of steps. There is nothing too fancy going on here. There's this g of f is actually the data misfit. So g appears here and here. There are also positive parameters tau and lambda that will affect the convergence of the method. They are not too difficult to choose. Much easier to choose than the regularization parameter. That's, as you may know, that's in inverse problems quite a challenge to find an automatic method for that. And then this PC, this is the projection to the non-negative quadrant, meaning that any negative element will be replaced by 0. So this has a mathematical convergence proof. It will compute the minimizer of this one. And then we use here just the Haar wavelet transform. Of course, you know, it's it has discontinuous building blocks. But there is some, I don't think this is maybe a deep mathematical fact, but actually several wavelet experts I've been talking with say that once they have proven theorems about wavelet approximations with great effort and lots of difficulty, they come up with a theorem showing some approximation property, of course using a mother wavelet having an appropriate degree of smoothness. Then they say that actually all these convergence rates always hold for Haar wavelet as well, although the theory doesn't cover it. So I think this is kind of a hint for the practical mathematician. It's always a good idea to try Haar wavelet first and see how it works. It may solve the problem already. Anyway, here that's what we use. We try this thing with Haar wavelets. And as you may know, wavelets divide the picture into vertical details, diagonal details, horizontal details at the small scale here. Then this is 2 times bigger details. And you can continue this division many steps. And in the corner, you always have the low pass part that's left over after all these detail scales. So then, like we saw on Tuesday, we get something that looks roughly like this when we compute a minimizer with the positivity or non-negativity constraint computation. This FB111, actually, let me comment on that. These B function spaces with 3 parameters are so-called Biesov spaces introduced by Oleg Biesov. There actually, this one here is related to the first derivative, first weak derivative. Like in Sobolev spaces, there's a weak derivative. So that's what this one is. And Biesov spaces have also P and Q exponents, similar to LP spaces, or maybe the Sobolev spaces that can be built over LP spaces. So of course there is some refinement because there is also Q in addition to P. But the way to think about B111 is that in total variation regularization, you are penalizing the one norm of the first derivative. Here you are doing something a bit similar. It's the first derivative and L1 norms are involved. It's not the same thing than total variation, but there is at least a hand-waving connection between those two. In the realm of Bayesian inversion, actually it turned out that this kind of using this norm in prior distributions behaves better with different resolutions than total variation does. In this context, why to use this space? It's nice because this norm can be written in terms of wavelet coefficients. In dimension 2, the B111 norm is just the sum of absolute values of wavelet coefficients. That's why it appears here. Okay. So then we are still facing the problem of choosing the threshold mu in the iteration. So you remember, if I go back a little, even here in the Dobeschi, de Vries, and de Mol, there is this mu parameter appearing here, which is the soft threshold, and the same operation is used also here. So how to choose this mu? Now, if we take quite small mu here, I'm writing mu j as if it would depend on the iteration. It doesn't here, it will later. But now we just have the same mu. Mu j is not depending on j, it's the same all over the iteration. And we see that the sparsity level of our iterate, so meaning what is the ratio of non-zero wavelet coefficients in the iterate, we see that almost all wavelet coefficients are non-zero because we have such a small threshold. We are not throwing away much of the coefficients. And then we see that almost all of the coefficients are used, and this is our reconstruction. Then if we put a much bigger threshold, then we are putting a lot of coefficients to 0. And you see the sparsity drops down to almost 0. Also, you see that not very many wavelets are used here. If we compare to the previous one, this is kind of much smoother. Then we go here. You see that the blockiness of the Haar wavelet transform can be seen. So the question is how to choose this mu so that it's good. It's the same kind of question how to choose the regularization parameter in Tikhonov regularization. So we propose this idea. We have one assumption. We assume that we know a priori the sparsity level, the true ratio of non-zero coefficients versus zero coefficients. How could we know something like this? Well, for example, in the medical application field, we can imagine we go to a hospital, we take they have a large archive of CT scans of people, of course. So assuming we get lots of those pictures, maybe anonymously, without patient data, we analyze them, we take the wavelet transform of all of them, and we just check how many wavelet coefficients are essentially non-zero. We hope that this is roughly the same number for all of them. Actually, in the case of the bone application I was talking about, we found out that it's roughly 65% in all of the samples we had. So then we think, okay, we know that this is 65%, or 0.65 in this case, and start using it. So if we know it for some reason, then we actually let the mu threshold depend on the iteration. So we let it change on the fly. And we drive it using a control method. So at each iteration, we see what is the sparsity of our iterate compared to the desired sparsity. And we let a basic, very basic vanilla controller to drive our reconstruction process. So if we say that we know that exactly half of the coefficients should be non-zero, we release our algorithm into the wild, and it will non-linearly adjust the threshold like this. So you see these sparsity values will be driven to the a priori known value. Yep.
You don't update the parameter in the first iteration, is that so? Keep it constant?
Yes, this one I did. Yeah, so I'm not updating. I chose, I think it's maybe 20. I just wrote there, start this controlling thing after 20 steps. That's why the direct part. Probably it's not needed, but in this coding I just did it to let the algorithm a little bit find its place and then start controlling. I'm not sure if that's really needed in general, but I just did it in this code.
And to choose this 20, how do you choose this number of iterations?
No.
Is there some?
There is no science behind it. I just, yeah. I don't think it's really needed. It could be 0, I think. And then if we change this, let's say 30% or maybe 30, so then again it will run here. And if we start with a different initial value here, a bigger one, again, so this will non-linearly drive it to the desired case. So now there are at least a couple of questions about this approach. One was actually asked by our referee, who asked, why don't you, if you know a priori that there is that many non-zero wavelet coefficients, why do you use this soft thresholding at all? Why don't you use hard thresholding and require that number of non-zeros at every step? I admit this is an excellent criticism of our work, and indeed one can do so. My only defense is that this approach actually can be used with, for example, total variation. There, the gradient of the unknown is sparse, and we could equally well think that we have an atlas of previous images. We can measure how sparse is the gradient there, and then we could you can take your favorite total variation algorithm that has a regularization parameter, and with the same idea, you can control that one and drive the sparsity there. So I think our idea is more general than just this kind of thresholding algorithms. That's my defense. I don't know, does it fly or not, but that's the best defense I have for that one. And then, of course, one could ask, can we prove that this converges? Now, in every computation we did, it seems to work very nicely. And my student, Juho Rimpeläinen, who has been writing these codes in his master's thesis, looked more into this. I asked him, do you see any way of proving something about it? And he said that there seems to be a problem because of the non-linearity of this process, of this thresholding algorithm. There are proofs for this controller for more continuous cases, linear cases, but for non-linear it's more difficult. On the other hand, and this is actually maybe another defense against this hard thresholding suggestion, because for this soft thresholding iteration, we have a nice mathematical proof that this converges for a fixed mu. So then, even if we don't have a good proof that this nonlinear strategy works, we could, as another weakish defense, I would say that we can first run it for a while without having a proof. But anyway, if we arrive at some mu, like we do here, some mu that is delivering the nice sparsity, we could freeze mu at this point. And then the rest, what happens with this soft thresholding, has a mathematical proof of convergence. Whereas the hard thresholding thing, I think, doesn't have. But anyway, I think it seems to be a useful approach. I hope it's an interesting approach. Anyway, somehow I would also say it kind of combines two very practical ideas in a way that seems to produce useful results. Okay, then we also wanted to look a little bit at shearlets, because shearlets, as opposed to wavelets, I mean, if we have, like typically in our target area, we have jumps on curves, maybe boundaries between tissues or otherwise between different domains where the attenuation coefficients has different values. So if we have a jump on a curve, wavelets are known to, when you represent a function that has a jump along a curve, you will need all the wavelets with all scales. And actually, you need, even for a diagonal curve, you actually need the wavelet coefficients for the horizontal, vertical, and diagonal detail. Shearlets have parabolic scaling, so they actually start to adapt, especially when they become smaller, they become more needle-like, and there you only need the coefficients for shearlets that are roughly aligned with the jump curve. So they maybe hold a greater promise. Let me remove this. Because also we will see that in X-ray tomography, especially limited angle tomography, there is a quite direct connection between your projection directions and the parts of the so-called wavefront set, which analyzes not only where the function has singularities, but also the direction of the singularities. So shearlets are really good for that. Oh, okay. So shearlets, let me just show you how they look like. They also divide the picture into different detail spaces. So first, at the coarsest scale, I show you the 8 parts, or 8 parts where the shearlets divided. So they look like this. Then we go to one step finer scale, smaller details, and the same number of directions, 8 directions. And then we go to yet finer scale, and now there are 16 directions. Like that. Shearlets divide up the Fourier space in this kind of boxes. So if you look at one shearlet, take any shearlet, take the Fourier transform of it, and that will be essentially supported in these kind of areas. For example, this darker green, these two pieces contain the essential non-zero parts of the Fourier transform of one of the shearlets with a smaller scale, and these are for a little bit bigger scale shearlet. And then the number of angles, to how many angles it's divided, the number of angles will increase when you go to smaller details. So it's that kind of a transform. It's not an orthonormal basis as the wavelet, for example, the Haar wavelet basis. These shearlets only they only make up a frame that kind of has doesn't divide the information in the image into orthogonal parts, but somehow the information gets distributed a little bit to different frame elements. So it's not, they are not completely independent, the coefficients, like they are in an orthonormal basis, but they have some connection. So this is somehow how we use the similar shearlet, controlled shearlet code in the same way than for the wavelets. We had to be a little bit more careful because we actually had to make sure that the approach also works with frames, not only with orthonormal bases. But I think now we have, with this, using these couple of papers I showed you and this a little bit more complicated iteration, there it works nicely. And this is what we used in 3D for the bone example with the controlled method of finding the threshold parameter. Any questions at this point? Yes?
The dimension of the space of this kind of wavelets.
Sorry? Can you?
The dimension of the space, how gross? Because originally you have a signal that has a certain number of states. When you apply wavelets, it keeps the number. But in shearlets?
There are more, yes. I mean, in the shearlet transform, there are more coefficients than there are pixels in the image. How much? It's a bit complicated. It is more. I think it also depends how many scales you choose to use. I will need to look that up after the talk. I don't know that by heart, but it's more. It's more, and the computation of the shearlet coefficients is a heavier computational task than the wavelet coefficients. I think significantly. On the other hand, also if you compare to so-called curvelets, I think the shearlets have a more efficient computational implementation than curvelets have. And then you get this wavefront set resolution, which has an immense theoretical value, and it seems that this can be also very useful in practice. Okay, at this point I would like to talk a little bit about the back projection operation, which is also known as the transpose of the matrix A, that appears in many places, and well, let me show you how it looks like. So just to remind you, so this is the Tikhonov regularization we already saw. So we have a penalty functional like the data misfit, and then something like this. There can be an operator here, for example, a discrete derivative here with f. And then computing the minimizer, one way to do it is to solve or apply this inverse operator. And you see here the transpose of A appears in two places. If you have an operator here, some L, then here you would have L transpose L as well. But A transpose anyway appears in this context. Also, if we look at, so on Tuesday we looked at one way of computing the total variation regularized solution. I then transformed the problem into quadratic programming, and then we used a standard QP algorithm. And I mentioned there are a lot of approaches with Bregman distances and very fine approaches in computing those. But then in my experience in practical tomography situations, when you can have millions of voxels and millions of data points, it may be impractical to use such methods. At least in my experience, the method that can be pushed to the largest scale that I know of is the Barzilai-Borwein minimization method. In my group, we have used this in several occasions, I would say with good results. And how this works, this is just almost like the steepest descent of Euler. But there, in steepest descent, you go along, you go to the direction of the negative gradient, and then you minimize along this one-dimensional line, and you go to the minimum point there. But it's well known that this is quite a slow strategy to converge. Barzilai-Borwein method makes it much faster. It always takes a step to the direction of the negative gradient, but the step size is computed in this way. And what is nice about the Barzilai-Borwein is that the memory requirement stays moderate because all the objects we use in Barzilai-Borwein have the size of f. So f is a vector, so we have vectors f, and we have the gradient of our function to be minimized, which also is a vector, same size of f. So we don't need any objects like the size of if f is in Rn, we don't need anything of the size n square, just size n things. Then there is, of course, the problem that the total variation penalty functional is not differentiable. It contains the absolute value function, so it's not differentiable. So here we use the well-known trick of introducing a small number beta, and instead of the length of the absolute value, we use this one, square root of element of f squared plus beta. So what happens here is so the absolute value function looks like this. So if this is x, this is absolute value of x. So now the idea is to use something which is asymptotically this one, but it's differentiable. Because the absolute value function is not differentiable here, but this red one is square root x squared plus beta. So just a trick to make it differentiable. Then, of course, strictly speaking, we are not minimizing the total variation functional anymore, something little different. But for practical purposes, I mean, if you are working with a really large scale situation, then the option is to compute nothing or to compute something with this kind of a trick. So then also Barzilai-Borwein makes it possible to apply the projection to the non-negative quadrant. If you want to try it out, there's the MATLAB code in the page I already mentioned before in my and Jennifer's book code page. But the point here is that the A transpose appears here as well because we need the gradient of G beta, and when you differentiate this part, A transpose will appear. And also, if we remember these iterations, well, this is the Loris and Verhoeven, very close to what we used before, it also has A transpose built in. So A transpose is something we often need. Let's take a look at what it really is, how to think about A transpose. So our system matrix A maps from Rn to Rk, so this is the sinogram space. The transpose, of course, maps from the sinogram space to the image space. Now, how to think about it? Let's see. So if we take such an image where there is only one non-zero pixel, and we take our X-ray data, we get a sinogram like this. But what happens if we do the same for a sinogram where there is only one point? Oh, sorry. So first, let's look at what happens when we map this one back here. Here we already a bit see why it's called the back projection. Because now, in the place of this non-zero pixel, we are sending back all the X-rays that are going through that point. You can kind of see here the X-rays in different directions in this geometry we are using. That's why it's called the back projection to one point. We are kind of taking all the information we have that's kind of traveling through this point. Also, we can take a look like this. If you put just one point here in the sinogram and map it here, we see that this is the path of one of our X-rays. Each point here gets mapped to a path of one of our X-rays in our measurement geometry, which is coded up in the matrix A, like we saw on Tuesday. So that's how to think about a transpose. It's sending sinogram elements back to the image space in the form of X-rays. And then you may remember this one where I showed how to construct the sinogram in this very small angular step kind of Radon transform style to collect the sinogram here of the Shep-Logan phantom. So here I'm making just a very quick derivation of the filtered back projection algorithm. The Radon transform, the classical definition goes like this. We have some line, any line in the plane, we can parameterize it in this way. So we take this line from the origin to the line that has a straight angle here. S is this distance along here, and theta is the angle here. Actually, we get two parameterizations for each line. I mean, we could also take theta that goes all the way here, and then a negative S. But anyway, this is the Radon transform, so it has an angular variable and a real variable, theta and S, and it's just the integration along the line that's specified by these theta and S. And then I showed you before this simple illustration of the so-called filtered back projection algorithm. Currently, I think all medical CT devices are based on variants of this algorithm. So I would just like to write down to you why is it called filtered back projection. This is only one of the ways to derive it. There are several equivalent ways of doing it. This is somehow my favorite way. So, so if we think that we have all line integrals of the function f available. So first, let's do this back projection operator, namely, at each point x, let's integrate together all the information we have around the point x, namely, let's take all the lines that pass through that point and collect together. These are the informations we have. So integrals of the function f on a line going through the point x. So t here goes from -infinity to infinity. So this is one of the integrals of f along a line that passes through x. And then let's integrate from 0 to pi with respect to this theta direction vector here. So then here we have collected together all the information we have in the line integral form near the point x. Then we can reorganize the function values a little bit what we are integrating. So instead of 0 to pi, let's integrate to 0 to 2 pi and compensate by not going from -infinity to infinity, but from 0 to infinity. Just a little reorganization how we look at the integrals, and also I'm multiplying and dividing by t. Then actually we can move from polar coordinates to Cartesian coordinates. Kind of a trick here, and then we see that actually we are dealing with convolution of f with such a singular function, 1 over length of the vector. Just a little trick with integrations. We see that we are dealing with a convolution with this kind of a weakly singular function. So then, of course, the convolution has a connection with the Fourier transform. On the Fourier side, it's just pointwise multiplication. The Fourier transform of 1 over length of y actually is 1 over length of xi. Then we can give a name to this operator that first Fourier transforms a function f, then multiplies by the length of the Fourier vector, and then inverse Fourier transforms. It's called the Calderon operator. So it's a pseudo-differential operator. It's kind of a first derivative because it grows linearly with xi, but it's actually not a derivative, pseudo-differential operator. So then we can see that actually this operation of TF we defined on the last page, on the Fourier side, it looks like this. So what we do, if I go back to the previous page, this one. So what we did here with the TF at the point x was to collect together all the information involving the point x, integrating together the information at all lines that go through x. And then actually, after some computations, we see that on the Fourier transform side, it's the same thing than this one. So how to find f from this situation? Well, if we multiply with length of xi, it will remove this guy, and then we just inverse Fourier transform. So we see that actually the Radon transform has the line integrals organized inside it. R star is actually pretty much the, well, R star is pretty much the same. R star R is the same thing that I call T. So this is what we measure in a CT machine. When we combine those integrals in a way just discussed, it's actually R star applied here. And then because of this formula, we see that overcoming this effect means multiplying by the length of xi. So this is the filtered back projection idea. And actually this R star, what that's doing is very much related to the A transpose matrix. But this part is really, I haven't, this is just a quick view of this one. This is not really the core of this course. I'm more concentrating on the sparse data approach, and this kind of filtered back projection is not so good for that. But for completeness, I wanted to say something about that too. Any questions about that stuff? If not, let's go forwards. And now I would like to tell you a little bit why limited angle tomography is an even more ill-posed inverse problem than full angle tomography. So, limited angle tomography, this is, for example, it means this. We are, like before, we are collecting this sinogram with this kind of sparse angle approach we did before. But now, let's say for some reason, we cannot go on. Previously, we went all the way around it and collected kind of all the way up to 180 degrees. But here, for some reason, we have to stop. So now we have such a matrix, which is, well, it's a part of the matrix we had before, kind of. And then if you just look at the SVD, the singular value decomposition, and the singular values, with the gray line, I'm showing you what we had before. We had 15 projection directions, but spanning the whole 300 or 180 half turn. Because of the parallel beam geometry, that's enough for full information. And here we have 15 angles, but spanning only from 0 to 90 degrees. The singular values here marked with red, they are a little bit worse. They are going faster small than the gray one, so indicating that, okay, we are dealing with a little bit more ill-posed problem. But that's not the whole truth, because actually we can also analyze geometrically what information are we missing with this kind of limited angle measurement. These properties were actually first analyzed in quite a general setting by Alan Greenleaf and Günther Uhlmann in this classic paper. Todd Quinto wrote this one. I highly recommend this to anyone interested in this because, well, it's a really well-written paper and concentrating on this X-ray tomography problem. So it's good for getting into this specific topic. And recently, Jürgen Friekel has worked with Todd Quinto and produced nice numerics and further results about this thing. So there is a precise geometric understanding. What can we see from limited angle data? And it's written in terms of the so-called wavefront set. So here we have our this CT phantom, which is piecewise constant, which jumps along the boundary here and also jumps along these letter forms. So I actually used shearlets to compute the specific parts of these jump curves that we can see or not see stably in the data. Namely, the theorems in these papers say that these parts that we are tangenting with X-rays in our measurement, those parts we can see. Very strictly speaking, actually, we should see. So if we have here such a shape, and if we want to, so the wavefront set means that at this point, there is a singularity in the function, but also the singularity is to this direction, because there is a smooth curve along which the jump occurs. So to detect this part of the wavefront set that contains both the location and the direction, we need the X-ray that's going through this point and has a straight angle with this direction vector, but also we need plus minus epsilon angles. So we need, in the microlocal analysis theory of this situation, so we need a little cone of X-rays tangenting and close by tangenting. If we have that, then we have stable information about these parts. Of course, in my example, we had also rather sparse sampling of the angular variable, which makes the connection with the theory a little bit imperfect, but that's anyway the way to think about it. Especially if we have quite dense sampling of the angle, then I think you can safely think that this is how it goes. I mean, this is what you see and don't see. So this is filtered back projection. If I go back and forth, you see we are losing the red parts. They are just not there. There is no information there. And even if we use, let's say, total variation, it's not recovering those parts. So those parts of the boundary are not in the data in any stable format. So it tells us if we want to do a reconstruction of those parts, it has to be based completely on a priori information for those red parts. The measurement data is not telling us about these parts. There's no way to recover from the data only. Whereas these parts are really well represented in the data. For those ones, we don't really need so much a priori information. So it's a geometric description of the information content of the data. Now, before we go to the dental imaging part, I would like to point out something important about this. If we are not interested in a perfect recovery of the whole image, but we are interested in seeing some parts of these jump curves. Now, let's say we do the reconstruction and we cut it. Let's say let's look at the reconstruction along a line like this. Then, because these blue parts are well reconstructed, we can see in the reconstruction where are the jumps along this line. However, if we look at the reconstruction along this line, we cannot expect to see where these jumps occur on our way cutting through the reconstruction. Like you can see here, if we go this way, we can see quite sharp boundaries in all of these places. If you go like this, it seems to be completely smooth. This is something important to understand with limited angle tomography. So let me next describe to you a product. I was part of a team that developed a product for dental X-ray imaging, actually making heavy use of this geometric property I just described. So this was a project done with many people. As you see, there was a really big group of people inside the company and universities in our Inverse Problem Center of Excellence. And the company where I started this work was called Instrumentarium Imaging. Then it was bought by GE Healthcare in 2004. Later, they sold out the dental technology part. That it became Palodex Group, and it was by this company that the product was launched. Tekes is the Finnish technology agency that funded actually 3 different projects between industry and academia that made this possible. Okay, so here the idea is we have a specific application in mind, namely dental implants. As you may well know, these days, if there is a tooth missing, the dentist will put in a screw. Sorry for the gross picture. I mean, this guy, it's a bad situation for this guy, clearly. But anyway, so here the idea would be to put a titanium screw like this, and once it's rooted there or attached, after some weeks or months, then a dental implant is attached into this holder. I made this picture black and white, so it's not quite as gross as the original. Okay, anyway, so how to attach this one is to drill a hole like this. So this is kind of a cross-section of the mandible. So if you cut this from here and look at how it looks like, so it's a cross-section. So the dentist needs to drill a hole as deep as possible to make the implant sturdy. However, there is a channel inside the bone. We all have it. It's going here inside the mandible. There are some nerves going there, and they shouldn't be damaged. If those nerves are damaged, I mean, if the doctor drills and damages the nerve inside the channel, so here is the channel, here you see the cross-section, there will be partial paralysis of the face, maybe chronic pain, could be an expensive lawsuit for the dentist. So it's better to not drill too deep. And also, let me point out that losing a tooth can happen to anyone. I mean, my friend Pasi went to the dentist, and the dentist said that we have to remove one of your mandibles. I said, oh, come on, I mean, it's one of my favorite teeth, don't take it. But the dentist said that, no, the situation with the roots is whatever, it has to be taken out, or soon you will have much worse problems. So you don't have to be a hockey player or a boxer to lose a tooth like that. So it's quite a relevant problem. Then, how to image, how to find out how too deep to drill. So here's a picture of how things were in 1918. At that time, an X-ray tube was used like this, and this patient is holding a film holder. So the idea was to take a small piece of film, put it inside a little holder in a dark room. Then the holder has some phosphorus inside. So when the patient is holding like this, X-rays are coming. The phosphorus inside is glowing, visible light, which will expose the film, and then it's developed. But in the old days, they had to do many of these. I mean, if the dentist wanted to see the whole dentistry, there had to be many of these. And the patient had to hold one here, then here, another one here, like 10 here, another 10 here. Very tedious. And then to develop all of these little pieces of film and lay them out on a light table. So it was quite tedious. So this man, Yrjö Paatero, a Finnish inventor, grew tired of this. He was responsible for University of Helsinki dental radiology in the 40s. And he got really tired with these small film pieces, and he started thinking, can we image all teeth at the same time in one image? Here's a part of his patent about the so-called orthopan tomograph he invented. The first machines looked like this. Now they look a little bit different these days. Let me show you. Maybe you know this, but let me show you anyway. So this is shot in the company I used to work for. This is Maria, my PhD student. So you see there's a machine that rotates around the head, and And the X-ray source is here, and detector is here. The picture that comes out looks like this. You have probably seen these. Probably many of you have even been in a machine like this, I think. It's a very basic tool for every dentist these days. And the machine has an X-ray source here, and here there is a narrow detector, 64 pixels wide, 2000 pixels high. And in the film time, there used to be a linear movement of the film that geometrically, ingeniously combined with the rotational movement so that it will pick out a sharp layer following the dental arc. In digital times, it's done by taking thousands of very narrow images and overlaying them with the same geometric rule that happened with the moving film and picking out a sharp layer. It's a form of unfiltered back projection if you look carefully at the geometry. Then we wanted to use this machine for drilling, for measuring the depth of the hole to be drilled. But it's not possible with this one because it has geometric distortion. One of the obvious reasons is that this picture is so strangely constructed that vertically it has a fan beam geometry, but horizontally it has parallel beam geometry. It's quite an involved thing how it's constructed. But we wanted to use this machine anyway, but we had to use it a bit differently. So we programmed a new movement, kind of like a scanner movement. It turns and scans with the narrow detector a picture like that because it can't take a two-dimensional picture. The detector is so narrow. Also, it can't go all around the head because it goes so close, as you saw in the video. It can't do this scanning thing with all directions. There's only this kind of limited angle of view. So we ended up with this mathematical problem. With the scanning movement, we could make it collect 11 images like this. So 2D images done by this scanning trick. Necessarily restricted to this opening angle of 40 degrees. If you look at classical papers on limited angle tomography, you know that this is a really bad situation. I mean, even if you go from 180, if you go to 150 degrees angle of view, the singular values already become really, really ill-posed. I mean, it's really bad. 40 degrees is really difficult. Also, let me comment that, like I showed you on Tuesday, I showed you these little Sudoku images, like 3x3 Sudoku with some numbers. We have the same situation here in principle. We have 3D voxels instead of the 2D pixels, and we have 7 million voxels in this volume of interest. And we have 11 pictures of 1 megapixel. So we have 11 million data, 11 million linear equations concerning 7 million unknowns. In principle, it's just a Sudoku like we saw then, but much bigger. And also it has the limited angle difficulty. So then, actually, it turned out that with this approach, because this is what the dentist wants to see, actually there are X-rays that are tangenting these boundaries that are to input. So here is the nerve channel, here is the top of the bone, and so here you can see the millimeters here. So there are a few things I would like to emphasize with this approach. First of all, the limited angle situation doesn't destroy this approach because we are imaging it from such an angle that the important boundaries we can see even from the limited angle situation. Another point here is that it's not necessary to have a perfect reconstruction. As an inverse problems mathematician, of course, we think, oh, how can I compute the function f perfectly? We cannot. It's too hard a problem, but we don't need to. The only information that the end user, the dentist, needs in this point, the only important information is how many millimeters. And even from this imperfect, you see there are kind of artifacts here and here. It's not a perfect reconstruction at all, but it's good enough. That's the point here. It's good enough for the end user. The end user can see the important thing, and that's it. It's good enough. Here is another reconstruction from the same target done with a cone beam CT, going all the way around, collecting a lot of data, making quite a perfect reconstruction. Also delivering 100 times more radiation to the patient. So the point here is that we can give the dentist the crucial piece of information by reducing the radiation dose by a factor of 100. Also using the machine that's already at the clinic. The doctor doesn't have to buy a cone beam CT that can cost like 100,000 euros or several 100,000 euros and to find space for a big machine. They can just make a software upgrade to the machine that's already at the clinic. The software upgrade has new movements and inverse problems regularization algorithm inside it. So also for the company, from the business point of view, I mean, they can sell a software upgrade that makes the old machine do a completely new trick. So I think here is somehow the mathematics is used in a nice way, in my opinion. We can reduce the dose, we can benefit the company, the dentist can work with the old machine. Kind of seems that mathematics is really useful in this case. And these are really used all over the world. There are thousands of them globally. Okay. So I'm pretty much now in the end of my talk. So in my book with Jennifer, we have, in the first part, we have a lot of stuff about this X-ray tomography. And we have a web page, which I already mentioned, but there are lots of MATLAB codes that you can just download and start using. Also, I also already advertised these ones, so the data sets are available at the website. Also, the Astra toolbox we are using quite intensively now in our group, and many groups globally are adopting these. So I think it's a good way to go, because it seems that the whole community is starting to go together with this Astra toolbox. Yeah, the TV Reg is a good one. Also, here are some books for those of you who are interested in this X-ray tomography approach. Several classics, and also Peter Kutschmann's new book has also nice historical review. And okay. So what should we do? There's still some time, but
so it's up to you.
Okay. You have a question?
Yes.
Okay, good.
Yes, perhaps one thing more for kind of completing the picture. Could you talk a little bit more about the soft and hard thresholding? Because it's something that appears here, and I've seen it appearing a lot also in Monte Carlo methods and other areas. So if you could say a few words about that, this might be very helpful, especially for students and for me myself.
Okay.
Yeah.
So I'm afraid I'm not really a deep expert on these thresholding algorithms. I have been more a user of them. My impression, which may be incorrect, but my impression is that the hard thresholding algorithm is something quite straightforward, and with the idea that, okay, let's just put small ones to 0 while iterating. And why would there be this soft thresholding operation at all? It's my understanding that when analyzing this minimization problem from the point of view of convex analysis, which is based on these primal and dual functions and finding the minimum, making use of these primal and dual worlds, there these proximal operators appear. There is a concept called proximal operator, and I think this soft thresholding appears as such a proximal operator. I would love to be able to give a better explanation, but I'm still learning this stuff myself too.
Yeah, that's very nice. The other question I had for you is you mentioned lots of MATLAB codes.
Yes.
And I myself I am a big fan of MATLAB and also Octave. But in recent years, there's been a lot of effort towards R and Python.
Yes.
And I was wondering if you could suggest, perhaps not now, but another time, some pointers towards the R world and if you have something on the top of your head.
That's actually something good. So R and Python, I've heard about them. I've seen colleagues use them, and I've also heard that in some aspects they may be really the best tools to use for some things. For me, why I'm bringing up MATLAB is is the practical reason that I've used MATLAB for more than 20 years. Actually, and all my scientific collaborators use it, and also all my industrial collaborators use it. So then it's, after having lots of codes in MATLAB, and also since the collaborators use it, it's easy to work together using the same environment. That's why my talks are so much based on MATLAB. There's no really deep reason for it. This is the reason. It's the reason that it's the thing I use the most. Maybe actually, since there is time, I could mention one curious thing about limited angle tomography. Like the other day, we had this mathematical theorem saying that if you have a finite collection of projection directions, you cannot see anything. That was the mathematical conclusion, which is in the practical world, it's not quite like that. Obviously, we can see a lot from finite data sets. With limited angle tomography, there is also a curious, it's a uniqueness result, saying that if you have limited angle data, so you have an object, let's say you have two objects, F1 and F2, and then for both of them, you have limited angle data. So you have X-rays to this direction and, let's say, to this direction, and all directions between them. So you have like angles if you have such a cone with epsilon angle, epsilon b as small as this, I mean just any positive number. So then mathematically you can prove that such data, such part of the Radon transform uniquely determines F. So if you have these two, F1 and F2, and their limited angle tomography data are identical for these directions between in this cone, then they must be the same functions. Kind of saying that if you have limited angle data with an arbitrarily small angle, you know perfectly the target, which is like the previous theorem was kind of pessimistic, saying that finite number of projections gives you nothing. This mathematical theorem says that any limited angle, even with a very small opening angle of view, you see everything. So how to think about this result? So now if you know the So you know this Radon transform for, let's say, theta, for all theta smaller than epsilon. So this is what you know. Then if you do a little Fourier transform computation, you actually see that if you have these line integrals with these directions, you can quickly compute that actually you know the Fourier transforms of f1 and f2 in such a domain in the Fourier space. So this is Fourier, this is the frequency domain, and you have such a bow tie shaped domain where again this is with epsilon angles. And because you know the Radon transform for these directions, you know the Fourier transform of f1 and f2 here. And now the Fourier transform of compactly supported functions is an analytic function. And you know an analytic function in an open set. So then you know the analytic function everywhere. That's why you know that, I mean, if the Fourier transforms of these two coincide in this cone, they must coincide everywhere. So this is the mathematical result. And then, again, the practical view is different because this information actually involves analytic continuation, which is well known to be very unstable in practice. Mathematically, you can, of course, just do it, but practically, it's very unstable. So then, and because the practical intuition is that if you are missing even a little bit of data, even if this is the part that you are missing, so you know all of this Fourier part and all of this Fourier part, already such a small cone makes difficulties in limited angle tomography in practice. So again, this is kind of an opposite situation in practice than it is for the theory. So maybe the point here is to remember that the connection between continuum analysis of the purely mathematical situation has a complicated connection to the discrete world of computations and practical reconstructions. So it's important not to get discouraged by theorems, or also not to get too much excited by theorems. First check what is the exact connection to the finite and discrete world of practical computations to make use of the theorems. Maybe that's the message of this analysis. Okay, so I think I will stop for today, and tomorrow, starting at 2, we'll have the third lecture, and then I will concentrate on sparse X-ray tomography imaging of moving objects. So thank you very much.
Okay, any questions or remarks? So, if this is not the case, Uri?
About this Barzilai-Borwein, why did you choose that method?
Barzilai-Borwein, okay.
Because it's chaotic. It doesn't bother you?
It
is chaotic.
Yeah, it is, yeah. So, no deep reason, again, I think. At some point when working at the company, I needed some method to start minimizing. I looked around the literature around the year 2000, 2001 or something like that. Then I stumbled upon this Barzilai-Borwein, and it started delivering useful results. And since then, I've been a friend of the method, while knowing that for sure there are other methods as well. Would you have some in mind? I mean, something else to use for this one.
People talk about something called a heavy ball and another one which is a Nestorov method that are more or less aimed at the same thing.
Okay.
Yeah.
Interesting. We have to take a look at those.
Actually, you're trying to minimize this functional along the search line, isn't it? That gives you the step.
No, we don't minimize.
Oh, the formula that you have for lambda k. How do you derive it?
Okay, of course, I think the motivation behind this definition is to try to minimize along the search line, but not really certain, like steepest descent will really go along the line and find the minimum. Okay. This takes only just the computer step size and just steps. Along one line, it's no analysis done along the line. I mean, that's the step size, and that will be the step that's taken.
Okay, we can discuss it later.
Yeah.
Josh.
I just wanted to make one comment. I really liked very much you going into this detail of the limited angle tomography case and comparing both the extremely hopeful situation of considering a very tiny angle and the totally hopeless situation of considering only discretely many samples. And I wanted to mention that there is a very deep, from the theoretical point of view, work that has been done towards determining the singular value decomposition of the limited angle. And that's perhaps a way of trying to look deeply into the mathematics of which relates to special functions like Gegenbauer polynomials and things like that. And there is a very classical work of Grunbaum and collaborators on that. So just to mention that this is interesting for students perhaps to pursue.
And Davis, I think the Davis on the nature of the on the Illposedness nature of the limited angle tomography problem. Yes. Yeah, maybe it would be good. I think I'll add a few references about it.
Okay. All right. Thanks a lot. Very nice.
Thank you.
Okay, this is it. Time is over. Thank you once again, Samuli.
Thank you.